Today, we have a lot of containers and microservices everywhere. Not sure if it's always useful, but at least it's very popular. And it's very important for these services to have small footprint and fast startup, that's clear. So what's the difference between native and Java applications, and why is this a problem for Java? So with native applications, we have the compiled code and the shared libraries. And when we load a program, all the code and the shared libraries is loaded into RAM. And only our working set of data is allocated from virtual memory. If we start 2 or 3 instances of the program, we only have the additional working set in the memory. All the other stuff, the shared libraries, the code, the data structures, they are all in shared libraries and they are shared across the processes. With Java, we have the problem that all our code is in class libraries. And we will have to load these class libraries, but at runtime, we will build up a metaspace which holds all this information. We just-in-time compile our Java bytecode, and all this data contributes to our working set, which grows bigger and bigger. And the problem is we cannot share this working set because it's unique to our process. If we start 3 Tomcats, we will have 3 times the working set, the metaspace of all our classes, all the 3 times the JIT compiled code, and so on. And to overcome these problems, of course, there are several techniques. One is class data sharing, about which I will tell you today. The other one is ahead-of-time compilation. That's subject for another talk. So both improve startup performance and can reduce memory footprint. So I will start with a short history of class data sharing, which is actually a quite old feature, which was introduced a long time before we had containers and microservices and all this stuff. It was actually already introduced 2004 with JDK 1.5. It was the Sun JDK at that time. It only worked for client VMs and serial GC, and you see on this restriction that it was actually, in the beginning, it was intended more for startup improvement, not so much for saving memory footprint. And it could only cache system classes. Then it became part of the OpenJDK with the initial OpenJDK 6.7 contribution by Sun. And since that time, a lot of work has happened on this topic. So in the meantime, support for server VM for the C2 compiler was added, support for various other GCs like G1, Parallel Old, and so on. Support for shared strings. I will explain that in more detail in a few minutes. And also support for application classes was added with JDK 9, but only in the Oracle JDK as a commercial feature. So you could only use that if you unlock the commercial features, which is only allowed if you buy a license from Oracle. But now with JDK 10, this support for application class data sharing was contributed to the OpenJDK with JEP 310. And it's landed in JDK 10. If you download an early access of OpenJDK 10, you will have it and you can play with it. Okay, so let's start with some basic functionality. How does it work? So you can just call Java -share dump, and this will give you some output. It will load some classes from a class list. This class it's a default class list which is hidden in your Java installation under Java home lib class list. This class list is actually assembled at the build time of the JDK, and it contains a well-known set of classes which is considered to be useful for many applications, for most applications. And these classes get loaded, and then a shared class archive is created. Again, inside your JDK home directory, you see that's about 18 megabytes big, and this contains a representation of actually mostly of your metaspace of these classes from the class list. You see one of the problems is that the shared archive is written into your JDK directory, so if you don't have write permissions there, it won't work. But we will see there are options to control both, also the source of the class list file and also the destination where the shared archive will be written to. This is just the default. If you call now a hello world, I called it hello CDS for this talk, and switch on share on to use this shared archive, we actually see nothing. Hopefully we see a startup improvements. We will measure that in a second. If we want to verify that we really use the shared archive, we can use new logging API, which was introduced with Java 8. And there is a special logging tag for class loading. So we say -xlog class load. And then we will get a line, an output line for every loaded class. And this every line will have a source tag for the location from where our class was loaded. So, excuse me, you see the Java-lang object class has been loaded from our shared object file. So that worked. But we can also see that, for example, other classes like the URL class path file loader was still loaded from the runtime module. So it was obviously not part of the shared archive. And of course, our example class, which we put on the class path, was also loaded from the file system and not from the shared archive. We can now grab to see how many of the classes from our Hello World program has been loaded from the shared archive. And we see in totally there were 477 classes loaded from the shared archive. And if you grab for the opposite, everything not loaded from the shared archive is just 5 classes. So for a toy application like Hello World, class data sharing works pretty well. So let's get some performance numbers, just a simple benchmark, startup benchmark with time. First we turn class data sharing off, and we see it takes about 160 microseconds. If you turn class sharing off, it's about 148, and it gives about 9% of overall performance improvement. That's of course the whole runtime. We can do a little better if you use the logging API, because that gives us a timestamp for the load time of every class. And if we get the timestamp of the loading time of our applications class, we can see how fast that was loaded. And you see that the application class, our application class was loaded about 13% faster. So that's not very much of an improvement, but anyway. So you may notice that the time here is a little bigger here than when we measured with time. That's because the logging, of course, incurs some overhead. And that's why these numbers are bigger than the numbers we measured with time. These numbers only measure the time until the main class was loaded. These numbers measure the whole runtime of the example application. OK, so now let's come to something more real. Let's see how this behaves with JRuby. So I downloaded the latest Ruby version. We have to export verify JRuby equals 1. I think this is because otherwise Ruby will just put all its classes into the boot class path, which is not how you usually run it in production. And there are also some problems with class data sharing if the classes come from the boot class path. So anyway, that's not so important. So we put, we say we want to switch on class data sharing. And for the purpose of verifying how it works, we again get a list of the loaded classes, and this time we don't want to have it on the standard output. We write it into a file, and then we start a JRuby -e1. So I'm not a Ruby programmer, but as far as I know, it's just the expression 1. So this actually only starts Ruby, and then evaluates 1. So it's just a poor man's benchmark for startup performance of the Ruby. So Ruby starts up and then it evaluates the expression 1, which actually is nothing. So when we do a word count on the file which contains all the loaded classes, we see that about 6,600 classes have been loaded. And when we grab for the classes which have been loaded from the shared archive, that's just about 1,000. And that's no wonder, because this was the default class list, which was assembled from the default class list file, and obviously that didn't contain the Ruby classes. So there is another option, which is called -xx dump loaded class list. This is actually the option you want to use to produce your own custom class list. You put it onto your command line when you run your application, and it will, when the application terminates, it will dump all the classes which have been loaded by the system class loader into this file. So when we run that, we see it's only shows us about 1,400 classes. That's because, as I told you, CDS by default only works with classes loaded by the system class loader. So only 1,400 classes have been loaded from there. So now comes the new application class data sharing, which allows us to also share classes from our class path, from our application class loader. Sorry, did I say system class loader? It's actually boot class loader. Only classes from the boot class loader. Application class loader and system class loader is the same, but the name is so strange, system class loader. So system application class loader, it's the classes from your boot class path, from your application class path, sorry. So okay, if you additionally switch on application class data sharing and we run Ruby again, we see that now 6,500 classes, so that's actually most of the classes now are in this produced class list. And we can now use, again, the dump command, this time with turning application class data sharing on. We now use the option shared class list file to hand over the produced class list to Java. When we used xdump the first time, we didn't give any options, so it took the default class list file. Now we want to use ours, which we've produced specially for Ruby. And then there is another option to specify the location of the produced shared archive. So that's actually the place where the shared classes will be dumped to. So you actually have the possibility to create shared archives for different applications and store them wherever you want and then use them with your different programs. Unfortunately, this option shared archive file is a diagnostic option. I don't know why, because all the other options are just production options. So this is why we have to unlock diagnostic options here. So when we run that and look at the created shared archive, you will see that this is much bigger now. It's 58 megabytes. So the default class, the default shared archive, which was created from the default class list with 1,000 class file, was just about 18 megabytes. So a lot of more data here. And how we can use this now? Again, we turn class data sharing on. We turn application class data sharing on. We specify the location of the shared archive. And one more time, we also get a class list. This is just for the purpose of verification. In production, you don't need that, of course. So when we see, when we check, we see that again, Ruby loads about 6,500 classes. And we see that now, with application class data sharing, most of the classes, 6,400, come from the shared archive. So for Ruby, application class data sharing works quite well. When we do some performance tests, again, we turn application class data sharing on and execute JRuby with the expression 1, and it's about 2 seconds. And if you do the same with application class, with class data sharing turned off, it's about 3 seconds. So that's 1 second faster, about 30 times startup improvements. I think that's quite okay. If you have some applications which call small Ruby scripts a lot, that may help. So Charles Nutter was quite happy about this. He tweeted yesterday, and he wants to put these options in his JRuby startup script and opened a GitHub issue for this. Okay, so far everything looks good. So now let's try more server-style application. So, by the way, all these experiments were done with early access of OpenJDK 10. So I downloaded Tomcat 9 and ngrinder, which is just a WAR file. I actually don't even exactly know what it does. But it's like a big WAR file which I want to deploy in Tomcat and just to see how it behaves with class data sharing. So it's Catalina options. We pass over options to Tomcat. And again, we want to use the class data sharing, and we want to dump all the loaded classes into a file. And with Catalina start, we start Tomcat. And when we look at the output, we see that Tomcat start with this one WAR file, ngrinder deployed, loads about 12,000 classes. So that's, again, double as much as JRuby. And again, when we grab for the shared classes with the default archive, we are no wonder, just 1,000 classes which can be shared. Then we use the dump loaded class list in order to produce the customized class list for Tomcat this time. And we see that we get about 3,000 classes, but that's still not a lot, right? But wait, we didn't use application class data loading, so that's only the system classes. So when we add application, use application CDS, with Ruby that helped a lot. But you see with Tomcat, that's quite disappointing. We get like about 300 classes more, but still only 3,000 out of 12,000 classes. So why is this so? The problem with Tomcat is that it doesn't load the classes from your application class path. It has custom class loaders, which are configured with properties and with configuration files, and they load classes from that location. And unfortunately, the dump load class list option doesn't help with this. It only helps with classes loaded from the boot class path and from your application class path. So what can we do? This is actually just the same experiment like with JRuby. I just created a shared archive with these 3,000 classes. It's again about 50 megabytes, no wonder. And using it with Tomcat, we see that from the 12,000 classes, we share about 3,500. So it's not very useful in this context. So again, what can we do? So application class loading, application class data sharing with a custom class loaders is actually something that was promised by JEP 310. So why doesn't it work? The JEP says it should work. Unfortunately, as I told you, the dump load class list doesn't dump these custom classes loaded by the custom class loaders by default. So we have to do some manual work for this. And we have to look at the class list format at the beginning. So if you look at the class list which you have produced before with dump loaded class list file, we see that's actually just a simple text file which contains class files on every line. So Java-lang object, obviously the first class which gets loaded, and Java-lang string and a lot of classes, and finally the bootstrap class, which is the init class of Tomcat. Unfortunately, the format for custom class loaded classes isn't specified anywhere. The only way to find it is to look into the source code, in the HotSpot source code, in the class list parser CPP file. So I've done that for you. And there we see that the class list file can actually be more verbose than just containing the simple class name. It can also contain a source tag with a URL, with a location from where the class has been loaded. And if it contains such a source tag, it also has to contain an ID. ID is that's just a unique numerical number within the class list file, and the class name has an ID. Every class name can have an ID, and also a class name which has a source tag must have a super ID. That's actually the class from which it was derived, and all the interface IDs of the interfaces it implements. So that's a little more complicated format, and doing that by hand would be not big fun. So how can we do that? If you played around with the Xlogging API, you may know that you can turn on different log levels. So until now we used xlog class plus load, so which gives us the info level of debugging, of tracing output. But we can switch to the debug level, and when we run it that way, we see that we get here the info output which we've used before to verify from where the shared classes have been loaded. But now, for every class, there is an additional line which is at the debug level, and you see on this line we get the class loader. So the null class loader is obviously the boot class loader, and we get the address of the instance class. So the instance class is the C++ representation of a Java class file. We will come to that in more detail in a few minutes. And we also have the address of the instance class of the superclass. So for object, that's null because object has no superclass. And you see, for other classes, the source is like a module, and this SQL module has been loaded from the platform class loader, not from the boot class loader. And then finally, our Tomcat classes, they get loaded from a jar file, which is not on the application class path, and this one is derived from object, and it implements several interfaces, and it was loaded by the URL class loader. So most custom class loaders are derived from URL class loaders. So this information is actually all we need to assemble our own class list file. Manually, we could do it simple like this. We just could misuse the address of the instance class and ID. That's just a numerical value. So we could put all the classes in a file with an ID. And for the server class, actually, we just specify the source location from the output, and we also give the IDs of the superclass. So you see that's derived from object. That's the same ID, and it implements some interfaces which are not in this list. So doing that by hand is cumbersome. That's why I wrote a small tool called class list for CDS. You can download it on GitHub. There's actually a link here in it. And if we dump now, if we start Catalina and dump the loaded classes on a debug level, we can now use this simple tool to produce from this class loading log class list file for class data sharing. And now we can dump a new shared archive, this time with the newly assembled class list. And if we do that, we see now the archive is double as big, so it's 100 megabyte now, 102 to be exact. And when we use this now by turning class data sharing on, and just for verification, printing the loaded classes, we see that from the 12,000 classes, we now loaded 9,300. So that's a lot better. Why it's not 12,000? We will come to that in a few minutes. There are still some problems for classes which cannot be loaded by class data sharing. Okay, so let's proceed. Now, classes is not the only thing we want to store in a shared archive. There is other things like strings or symbols. Symbols is actually just HotSpot internal representation of strings from your class file constant pool. And with strings, I mean Java-lang strings. So the VM uses a lot of strings for internal working as well as for your application. And it may be worth storing this additional data in the shared archive to share it across different instances. Because strings are constant, we could share them. So this is actually an extension of JAP 250. And it was available in a commercial version of Oracle Java 9. And with the contribution of application CDS to the OpenJDK, also the additional string and symbol sharing was added. Again, there is nearly no documentation available how to do this. You can find the bug where it says document how this works, but the documentation has only been added to some commercial Oracle documentation, not to the OpenJDK until now. So, in fact, what this documentation says is that you have to assemble yet another config file with a list of strings and symbols, and the exact syntax of these strings and symbols can be found out by using the J command with string table and symbol table. So let's do that. When we can just use J command with pgrep. We find out the process ID of our running Tomcat process, and then we say we want to dump we call the J command command string table with the verbose option, and when we do that, we get a long list of strings. So this is actually the PID, the process ID of our Tomcat process. That's just the version information, and then we have every intern string, to be exactly, every intern string of the VM will now be dumped to the output, and it's just the length of the string and the string itself in UTF-8 coding. And then we can do the same for the symbol table. Again, we get the process ID, and here we have two numbers. First one is the index, another one is the reference count. So symbols within the hotspot are reference counted, just printed out here, because jcommand is actually a debugging tool, but they just misuse this output for creating the shared archive config file, so that's not important. And then we have, from this information, we can now assemble a new config file. It has to have this header, like version 1.0, and then we introduce with add section the string table section, and then we verbatimly copy all the output of the string table command from jcommand in there, and then we have the symbol section, and we verbatimly copy the output from the symbol table debugging command there. And how can we use this? Well, again, we have to use the dump command. This is how we used it before with our customized class list, which we produced with CL4CDS. This was 102 megabytes. It's just to repeat this. And now we can additionally say we want to share all the intern strings and symbols from the Tomcat process. And when we do that, we see that it's slightly bigger, so 4 megabytes. We have another 4 megabytes of data which we can share. So enough command lines for now. Let's do some graph. So for Tomcat, I also did some startup performance tests, but for Tomcat, on my box, it took like 15 seconds to start, and I didn't see really any improvement. Like some milliseconds, that doesn't count when the whole startup is like 15 seconds. So for Tomcat, I am more concentrated on memory savings, and you see the red bar. It's using Tomcat with class data sharing turned off, and inside a Docker container using Docker stats, and this Docker container only executes Tomcat with ngrinder, and Docker stats tells us that it's about 221 megabyte. There's the whole command line here. You don't have to read that. If you're interested, you can look it up in the slides later. It's the exact command line. Yes, the blue box, dark blue box is class data sharing on. So we see that we save about 50 megabytes of RAM according to Docker stats if you use class data sharing. And if you additionally put in the strings and symbols into the archive, there is another 5 megabytes which we can share for one instance of Tomcat running in Docker. So Docker stats is not the only tool you can use. There is pmap. Pmap actually gives you very detailed, pmap minus XX gives you very detailed information of every address region your process maps, be it virtual, resident, shared, and so on. We will look at some more detailed logs at the end of the talk. So we have the same two processes here. And now we look at them with pmap, and you see that pmap actually reports a much bigger number for the resolved set than Docker stats for the same PID. And that's because Docker stats actually gives you the size of the dirty virtual memory, so the one which cannot be loaded from files. It actually more or less reports the private dirty section of pmap. Most people look at the resolved set, but that's actually not true. If you have many applications running, the resolved set is usually too big because it doesn't account for the shared part of the memory data. And here I have detailed the resolved set into private dirty, private clean, and shared clean data. And you see there is a lot of data which is private but which is clean, which means it was loaded from a shared library or from shared object, but it hasn't been changed by the process. And why this is important can be seen when we start a second instance of a second Docker container with the same application running. And now we have here two Tomcat processes running within Docker with class data sharing turned off. And you see the there is some shared memory in these processes as well, but it's just about 28 megabytes. So that's actually the Java executable, the libjvm, the shared libraries which are part of your Java distributable, but not much. And with class data sharing turned on, you see we have a huge amount. It's about 108 megabytes of data which can be shared. And this is actually the metadata from the shared class archive. And you see again, this private dirty part here corresponds pretty well with the Docker stats output. Okay, so I really had a hard time assembling these numbers because it's so hard. You don't get stable results, and the problem is, I called it the footprint performance uncertainty principle in HotSpot. You can run interpreted, then your execution time is very slow, but your memory consumption is stable. If you start using client compiler, you will see that every run you have like 10 to 20% differences in the amount of native memory use. That's because just-in-time compilation is so dynamic. One time it uses more, it compiles it inlines differently, it uses more, it uses a lot of native data structures which are stored in a heap, and your results vary very much. And then if you use tiered compilation, you have two just-in-time compilers, C1 and C2, and they can really use huge amounts of native memory. Like, it's not unusual that a compilation task of C2 takes about 1 gigabyte of native memory. So, like, maybe one detail here, these measurements were done with xint and with a heap of 64 megabytes only. So if you with a heap of 64 megabytes, you get like several hundred of megabytes native memory usage because of JIT compilation. That totally spoils your picture. So I wanted to concentrate on memory savings here. That's why I did it in interpreted mode. Okay, so this was more the high level part of the talk. So now I will try to explain you which of the data structure in the metaspace get shared and how this is done. For this, we have to look on the internal representation of the metadata in a hotspot. So we start with a simple class foo. This is the Java heap here. This is the metaspace. And this is the code cache. It's not so important for this talk now, but for ahead-of-time compilation, that's actually the part which could be shared by using ahead-of-time compilation. So as I told you before, as I mentioned before already, every class foo has a counterpart in the metaspace, which is called instance class. There's a lot of text here. It's just the name of the fields. You don't have to read that. Just try to get an overlook. So every class has a representation in the metaspace. It's called instance class. And actually, from the class header in the Java heap, there's always a link to the instance class. This instance class is actually quite sophisticated C++ objects. Every instance of instance class has a different size because they can have variable parts like the oop map, the v tables, the I tables of the classes. They are all stored in this object. So every instance of instance class is sized differently. And then every instance class has a backlink into the heap, which contains the so-called Java mirror. That's actually the class object for your foo instance. So when you call get class on an object in Java, you will get the instance class actually. But this goes around through the instance class. And then again, there is a backlink link from the Java mirror back to the instance class. It's all linked together. Then all the instance classes which get loaded by a class loader are linked through so-called class loader data. And for every class loader data in the metaspace, we have a link in the heap for the class loader Java object, which corresponds to the class loader which loaded this class. And you may know every class loader then contains a vector which links all the classes it's loaded. That's necessary to prevent them from being unloaded during GC. And then again, every class also has a backlink to its class loader. And then, to sum this up, every class loader data is then in another linked list, the so-called class loader data graph, which is a list of all the class loaders. So this class loader data graph is used, for example, by GC when it computes the roots or when it wants to walk all the loaded classes. This can be done from the class loader data graph. So the instance class has a field, a link to another data structure called constant pool, which is actually a representation of the constant pool of a class file. So a class file, a Java class file, contains the bytecodes. So most people just think about the bytecodes when they think about a class file, but it also contains a huge amount of symbolic data, which is in the constant pool. It's the name of the functions you call, the name of the classes you load, the constant strings which are used in a class, and so on. And again, this is a variable sized instances class, and for every constant pool entry, it has a link to a symbol which is stored in a global symbol table. This is all actually the symbol table, and the symbols are not really in metaspace. They are metaspace objects, but they reside in native memory alongside the metaspace. And then the constant pool has another link to a constant pool cache, which is actually contains the resolved versions or the resolved versions of the constants from the constant pool. So think about, you have an invoke virtual call in your Java bytecode. In the Java class file, this just invoke virtual just references the name of a method. That's just a string. When the interpreter the first time executes an invoke virtual, it looks up the class and the method from the constant pool, and then it stores. It can store the instance class instead of the symbolic instead of the symbol. So the symbols may be changed to the actual instance of that class to speed up the next invocation. And this constant pool cache then has another link into the Java heap, which is a pointer to an object array. And this contains all the resolved references. For example, strings, intern strings I was speaking before, are stored in this object array, in the Java heap again. And also, once such a symbol is resolved, it gets entered into the string table, which holds the intern strings. Also, when you do call string intern on your own string, you can enter it in this string table, which is stored in the metaspace, and that has a backlink to the heap to all the strings. Okay, and then the instance class has another field which links to the method data, and the method data finally contains the constant part of the methods, which is actually the bytecodes. And all this information, so most of this information is things we want to store in the metaspace. Because every time a class gets loaded from the class file, all these structures have to be created, allocated in native memory. Also, classes like the mirror class and the resolved strings have to be allocated in a Java heap, and that's a lot of time. And if you store that all in the shared archive, that's time we can save at startup, and that's also memory which we can share across processes. Yeah, then as I told, the methods then get compiled to code cache, but that's for AOT. So I didn't show you the whole picture when we used the xshare dump in the beginning, because I didn't want it to confuse you right ahead. So actually, if you run share dump, you get even more than this. You get even more than this information. But I want to show you some of it and explain you, because now that I showed you the big picture of what gets shared and how this happens, we can understand this better. So we see that the Java shared archive is allocated at 32 gigabytes. So that's actually 8000. That's 32 gigabytes. And then all the loaded classes, all the classes which we want to share get loaded by default from this class list file, but you saw we can control that on the command line. Then all the classes get verified. If you want to know how this happens, go to Nikita's talk. you see this was from the first example from our Hello CDS program. It's about 1,200 classes which have been which got loaded here. Then information which cannot be shared across processes is removed. Embedded pointers are relocated, so all the pointers inside the meta space have to be relocated to actually this address, because that's the address where the shared archive will be mapped at runtime. And actually this address can also be configured with a command line option if this for some reason doesn't work. Because you have something at this memory location, you can create another shared archive which is on another address, virtual address, and configure that. By the way, if it doesn't work at runtime, you won't get an error. It will just load your classes from the class path as usual. If you use xshare on, you will get an error. There is a third option, xshare auto. If you use auto, it will fall back to loading the classes from the class path. If you use xshare on it will stop on failure of loading shared classes. Then the symbol table and the string table get dumped to the shared archive. So you remember the symbol table was the HotSpot internal representation of the strings, and the string table were the intent strings. And now the intent strings are actually part of the heap. So how can a part of the heap be part of the shared archive? That's actually two things. So as I told you before, sharing of strings only works with G1, because in G1 you can have pinned regions. So you can actually map a part of your shared archive right into the G1 heap, allocate some regions there, and tell G1 to never GC these regions, because that's intent strings. And it's actually even more complicated. We have two different pinned regions in G1 which we can use. One is for intent strings, which are constant and which won't change. So they get mapped into a read-only heap region. And then we have other data structures, like, for example, class instance or the object area or things like that, which actually could be modified at runtime. And they get mapped to a read-write region in pinned region in G1. So here we are. So this was the symbols and the strings, which get into the constant heap region, and then we dump all the other Java objects which get shared in the shared archive. We remove the Java mirror because that's a Java that's a link back to the heap which cannot be shared, and then we get a layout of the shared archive. So it starts at 32 gigabytes with some small bookkeeping information. Then we have the read-write part of the shared memory. We have the read-only part of the shared memory. Some other data. So actually, this is the original data. This is just the bytecodes of the class file, the verbatim copy of the class file bytes. They get also dumped into the shared archive. And then we have the two parts. You see the different address here. That's part of the Java heap. We will see that later when we look with PMAP onto the process. So these are the open and the closed and the open part of the G1 heap regions. And it was, as I told you, for the default classes, to 18 megabytes of data. So when we run the Docker container, which I used to do the memory statistics, we just map the internal port 8080 to our port 8080, and we give Docker about 500 megabytes, and this is actually the Docker container with Tomcat and OpenJDK. And then we run pmap xx on this PID of our Tomcat in Docker, and you see now this is the memory layout of our running Java process. So this is actually the Java executable, which is quite small, get mapped at this address. Then we have the Java heap. It was just 64 megabytes. I told you I did the benchmarks with 64 megabytes. So this is a little less than 64 megabytes. And that's because now you see as part of the Java heap, we map in parts from our shared class archive. So this is actually the shared class archive which we've created. And we have here read-write parts of the heap, and they get mapped right into G1 heap. And these are then the other parts which start at 32 gigabytes, some bookkeeping information, then the read-write part, 22 megabytes, the read-only part, 39 gigabytes, and this was, I think, this is the also some. It's actually 2 read-only parts. Now, just pay attention. We start a second Docker container, and obviously we have to map its internal 8080 port to 8090. So this is the second instance of Tomcat running in Docker now. But we take the pmap from the first Tomcat which is running. And when I flip this forward and back, you can look at the shared clean and private clean sections, and you see that now actually all this memory in this column, this is shared between the 2 processes. So if you start 10 Tomcats, they will all use this part of the memory. And you see for the read-only parts, everything can be shared, obviously, because the process cannot change the data. But there are still like read-write parts in the shared archive which get touched by the process. So then only a part of this 22 megabytes can be shared, and because every instance changed them. For example, in the instance class, if you remember the instance class picture, there was a backlink to the Java mirror. So every Tomcat instance running has its own Java mirror. So it has to patch the instance class in the shared archive for every instance to point to its own Java mirror class. That's why these pages get dirty, and then they cannot be shared anymore between the processes. So for example, the Java bytecodes, you may think they are constant, but they are actually not stored in the constant part, because think you want to place a breakpoint. Into a Java method. This is done by rewriting the bytecode. So you actually still need the possibility to change the bytecode. So that's why the bytecodes are placed in read-write memory. So it's actually one of these sections here. You see here we didn't use any breakpoint, so that's why all is shared. But we still have the possibility to do it. If one Tomcat process would change the bytecodes because of rewriting or because placing a breakpoint, just the corresponding pages of that method would not be shared anymore, but all the other still can be shared. Okay, so I just explained you why some of the parts of the archive have to be read-write. And one of the problems was, for example, that we have backlinks into the Java heap. So just 2 weeks ago, a new feature was added to OpenJDK 11, to the development branch, and it's support for caching class mirrors. So if you still with me, that's actually this part of the Java heap, which can, after this change will be submitted, which can also be shared now into the shared archive as part of the pinned regions in G1. So it's not only the strings now, which can be shared, but after this change, we can also share the class mirrors. So this will make it possible to move more parts of the shared archive to read-only regions and to make them shareable. Okay, there are some limitations with AppCDS. Just a brief list here. You can share classes which were before Java 1.5. And you may think that that's not a problem. I don't use Java 1.5, but for example, about 1,000 classes of this ngrinder war file, which was the latest version I downloaded, are pre 1.5. So they couldn't be shared because of that. Because they have some dependencies on old libraries and they still package it together, for example. Then you cannot share dynamically generated classes. That's obviously because when a class loader, for example, generates classes at runtime, the dump step has no chance of dumping these classes to the shared archive. So the dump process, unfortunately, is a static process, as you saw in all the examples, we don't run the application when we dump the classes. First, we run the applications and create a class list file. And then in a second step, in a static step, the VM just loads all these classes without running the application and dumps them to the shared archive. That's unfortunate. We will see that on the last slide that OpenJ9 VM does that differently. But in HotSpot, it's currently implemented this way, so that's why we cannot dump dynamically generated classes. So another restriction is that all the classes have to be in jar files and not in standalone class files. But I think that's something which can be removed. I already tried it, and it should also work from class files. I think that's an artificial restriction. Yes, and also the interpreter might get slower because we can't do bytecode rewriting anymore. Because one performance feature of the template interpreter in HotSpot is that it rewrites bytecodes, for example, loads or invokes, as I told you before, to not do all this symbolic resolvation of symbolic links from the constant pool every time it executes a bytecode, but do it just one time, and then it rewrites the bytecode to a new version, to an artificial bytecode, which is much faster. If you do that, all the sharing of the bytecodes would fail. That's why bytecode rewriting is switched off when we're running with class data sharing. But usually that's not a big problem because after some invocation methods get compiled anyway, and then we won't see any performance degradation. Okay, so and this is actually my last two slides. My talk was actually about class data sharing in HotSpot, but IBM J9 has this feature as well since a long time, and you may know that IBM J9 has been open sourced in the Eclipse project as OpenJ9. That's actually a very cool virtual machine. It was the clean room implementation of Java. It's actually just the counterpart of the hotspot. So Eclipse OpenJ9 still uses the OpenJDK class library. You can download it from the Adopt OpenJDK project, or you can even build it yourself by just cloning from the Eclipse Git repository. And then the configure step will automatically download the class libraries from OpenJDK and build it with OpenJ9. And the nice thing about the class data sharing in J9 is that it seems much more elaborate. You don't have to do all these manual steps. And it's very well integrated with just-in-time or ahead-of-time compilation. So it also shares the ahead-of-time compiled data in the shared archive and also some JIT counters, which is very, very nice. They also dump the classes right at runtime, so you don't need an extra a static dump step. You just run your application with the xshare classes option, and it will dump all the classes. And this way, you can also dump dynamically generated classes, even classes from custom class loader without any hassle. And that's because they have patched the URL class loader class to be aware of their class data sharing. They even have a Java API which you can use to make your own class loaders which are not derived from your class loader aware of the shared classes. So that's very nice, very interesting if you want to experiment a little bit. So I will just briefly show you how to use that. You can specify how big the archive can get at maximum, and then you use the xshare classes option. You say where the shared archive will be stored. You also can produce different archives with different names. You get some output here, and there is, you see the archive is, they always create the maximum size of the archive, even if not all the size is used. So that's 128 megabytes. And then you can use the print stats option to xshare classes to have a look. So this is actually equivalent to the output we got at the dump step in the hotspot. We can get this after we created the archive for the IBM J9. And you see here, they also have like ROM classes. That's actually the read-only part of the metaspace from J9. That's actually that big. Then you see that by default they store ahead-of-time compiled code, about 13 megabytes for this application. It stores some JIT data. So JIT data is, as far as I know, it's the performance counters of your methods. So next time you start your program, you just load the performance counters and can JIT compile your methods right ahead without having to go through interpreted mode and gather profiling information. Yes, and the cache is, how much of the cache is full from this 128 megabytes. And this is just a small comparison. Again, I put the exact command line flags below if you're interested. So here I actually switched off JIT and ahead of time compilation in OpenJ9 sharing because I only wanted to show you how much memory can be saved. So you see in total, J9 has a slightly lower footprint than HotSpot, and it also saves some a certain amount of memory by using class data sharing. Not that much because they are comparable to HotSpot because their read-only class part is a little smaller than the set used in HotSpot. And as far as I know, they also don't share part of the heap, as is done in Java with the intern strings and now with the class mirror and stuff like that. So if you run this with ahead of time compilation enabled and JIT enabled, the startup improvements are quite good. You get even for Tomcat like 20-30% startup improvement and 20-30% less memory footprint altogether, which is quite nice. So that's actually all from my side. If you have any question, I'm happy to answer. Yes, please.
One not so question. Can you recall what can I do with Java 8 without
you can only use the normal CDS without application classes, so that only shares the classes, your system classes, which get loaded by the boot class loader. That's the only thing you can do.
And I can see on limitation it is not friendly for huge pages in Linux.
Yeah, that's true. Yes, because that's one of the restrictions. You cannot use it together with shared spaces because how it's currently implemented, it's just two orthogonal features that how the memory is allocated and mapped in the heap and in the meta space. Maybe that can, I mean, the huge page support in HotSpot is broken since a long time anyway. NUMA and huge pages really doesn't work very well. There is a JAP for that and there is a lot of bugs open, but until now nobody started really seriously working on it. But that's definitely an area which needs improvement in HotSpot, huge pages and NUMA support. Yes?
So I have a little question about verification of classes. HotSpot verifies consistency of... question about how HotSpot verifies that application classes or jars are not changed. And how it reacts on changes in shared classes.
Yes, so I didn't mention that, but yes, when the classes are dumped to the shared archive, a hash is computed of every class, and then when you call define class at runtime, this hash is verified, and if it's not the same, it will just use the original bytes at runtime.
Am I correct that it's done on per class basis, not per jar? This verification is done for every class, and one jar can contain some shared classes and some non-shared.
Yes, yes.
Thank you.
But I think for the boot class loader, I think it's done on a module basis. I think that's one of the restrictions why you cannot load single classes, just classes from jar files, because of this. But yeah. I think you can turn it off and on.
So, thank you.